In the second video on using R for ARIMA modeling, I'll have a look at how to model seasonal data. Now the example I'm going to use again is taken from the book by Enders. The example starts on page 99 of the third edition if you want to have a look at it. And he models and forecasts data on the M1 money supply in America. Now the data is available in an Excel file that you can download from Enders' website. It's called quarterly.xls. So I'm going to read that in using the read Excel package. So I'm loading that up and then using the function in there read_Excel. We can read in very easily an Excel file. I'll now load up the forecast package, which I'll be using again for the analysis. Now the variable within the quarterly.xls file that I want is called M1 NSA, which stands for it's the money supply M1, not seasonally adjusted. So it will have seasonal patterns which we need to model. As you can see, it's quarterly data beginning in 1960 quarter 1. So I'm going to read that in. Notice I'm using the pipe here. I'm doing that a lot here. If you're not sure how to use the pipe, have a look at my video on this. So I'm reading this M1 NSA variable and creating a time series object. Okay, so that's stored in the variable object M1. Let's plot that out. Just have a quick look. And as you can see, it's clearly non-stationary. It has an upward exponential increasing trend and almost certainly will have seasonal patterns. So we're going to have to transform it by taking the log to straighten out the trend. But that will then, there'll still be a trend. It will be a linear one, so that will need differencing. And also any seasonal pattern will require some seasonal differences. Now, one way to find the seasonal pattern is to look at the ACF and PACF, but another graphical way you can look at is using the function ggSeasonPlot, which is in the forecast package. This will plot the data for each year by quarter, so you can see there's a distinct pattern within each year through the seasons. So I'm taking my data M1, then I'm restricting it to a subset of about 11 years here, the 1960s, and then putting that into ggSeasonPlot. So this is the pipe operator, of course. So as you can see, there's a definite seasonal pattern here of the money supply increasing over the year, reaching a peak in the fourth quarter. Now I only looked at the first 10 years here because if you run ggSeasonPlot on the whole data, there's far too many lines to see what's happening. So just to confirm that that seems to be the case, I'll run it again here for the next 10 years or 11 years, the 70s. And again, we see the same picture of the definite seasonal pattern here of it rising throughout the year into the peak in the fourth quarter. So there's a definite seasonal pattern here. So in order to, first of all, remove the trend, the upward trend that we saw, I'm going to, well, first of all, take the log and then the first difference. So again, using the pipe, taking my data, then logging it, then taking the first normal difference, non-seasonal difference, then putting it into ggTSDisplay, which I looked at in the previous video, which of course draws the actual data and the ACF and PACF, which is a neat, so we can see all the thing together. So that's, as we can see now, it looks as if the trend has been eliminated, but notice these spikes here at 4 and 8 and 12 and 16 and so on, which of course is indicative of that seasonal pattern with it being quarterly data. So to remove that, of course, you need to take a seasonal difference, a difference between values which are 4 quarters apart. So I'm doing that here. So again, M1, logging, first difference, normal difference, then the seasonal difference, notice how you put that, and then into ggTSDisplay again. And we have now what looks to be reasonably stationary data. That's clearly no trend there. Those correlations at 4, 8, 12 and so on have disappeared. You still got one here at 4, but that's indicative of this, and that just tells us what kind of model we were going to estimate. Now, as far as ending up with this data here, it doesn't matter in which order you do the differencing. You could have done the seasonal difference first and then the normal first difference. And in fact, many texts recommend doing seasonal differencing first, because that may actually be sufficient to create a properly stationary series. Enders does it the way around I've done it here, takes the normal first difference first and then the seasonal difference. But whichever way around you do it, you'll end up with this data set here. So by looking at the ACF and PACF, he comes to conclusion that there are 3 possible candidate models, an ARIMA 110 and then 001. Of course, with seasonal models, you have to specify the values of P, D and Q for normal differencing, and then the ones for seasonal differencing. So the first model he estimates here is an ARIMA 110 and then 011. And of course there would be a little subscript 4 to indicate, if you know the notation for this, to indicate that it's quarterly data. So I can estimate this model using the ARIMA function, once again with a capital A, from the forecast package that we used in the video on non-seasonal data. The key difference is that, as well as specifying this option order equals for the non-seasonal P, D and Q, then you have to specify seasonal for the seasonal ones. So this first model has one autoregressive element at lag 1. We did, of course, take a first difference of a normal first difference, so that's there. No moving average elements here. Then seasonal, again, no autoregressive seasonal elements, one seasonal difference, and then one moving average seasonal coefficient, seasonal value, which will be at lag 4, of course, because remember this is the season element, so that is 1 at lag 4. So this is the model that we're estimating. Now again, to make sure to get the same results as Enders, I've had to specify the method equals CSS like I did in the previous video. And also what I've done here is that Enders in his text seems to include a constant, although other texts and other writers suggest that they shouldn't generally be a constant if you've had the difference. In fact, what I found was that including this term here, this option include .constant equals true, made no difference if you whether you include that or not. The results are the same, and I think that's because, as Enders says in his book, the constant is in fact insignificantly different from 0. So I've included it here, but I didn't bother in the next models. So again, notice the use of the pipe. So I'm calling this model 1, and that gets firstly the data, which is then logged, and then I'm restricting the start here. This is in order to make sure everything is over the same sample period. I've talked about this in the previous video, that in order to compare models, they must be over the same sample period. And then I'm feeding this subset of data, which has been logged, into the ARIMA function, specifying the correct values of P, D and Q, and capital P, D and Q here, the method, and then finally this thing, which I say is not really necessary. So running that, and then printing out the results, this is what we get. And if you look in Enders, you'll see these are exactly the same values. So there's the one autoregressive, normal autoregressive element coefficient, which is this one from here, and there's the seasonal one, which would be at lag 4, which is this one here, the moving average. Now, calculating the residual sum of squares in the AAC and SBC as in the previous video. So we get that. This for the AIC, SBC. Again, I'm just using the basic formula which you've seen before, which you can find in Enders text or any other. And these again are the same values as Enders, of course. Now let's do because of course the model's no good if the residuals are not white noise. Let's use the check residuals function that I did previously to check the residuals for white noise, and I'm going to do a Young box test with 4 lags as well. So running that, as we saw in the previous video, this is a very nice function in Forecast which will plot the residuals, plot the ACF and a histogram, and also run a Young box test. So looking at these, they look okay, apart from that one at lag, what's that, lag 10. So the first 4 look okay, so we'll probably find that this Young box test of 4 correlations is okay, yeah, fine. Again, notice how it modifies the degree of freedom according to the model degree of freedom. That's clearly not less than 0.05, so that's okay. What about 8 lags? Again, notice plot equals false, so I don't get the graph again. Yep, that's fine, in fact. And 12 is fine too. So this model seems to pass the tests okay, but of course it may not be the best, so the models may also have residuals which are white noise and have lower values for AIC and so on. So the second model that Enders estimates is this one here. It's a 110, 110. So we've got one autoregressive element here and one seasonal autoregressive element, no moving average element. And of course we've got the same differencing, a normal difference and a seasonal difference. And again, I'm doing this on the log of the data, of course. And notice I haven't bothered with the include constant equals true here because it doesn't make any difference. So running that, printing it out again, same as Enders. Here are the goodness of fit measures. Notice they're not as good as model 1, 0.02, this was 0.017. The AIC was -735. This is -701. Remember, the lowest is the best. Now, are the residuals okay? As you can see, that one looks a problem. That one looks a problem. That one, so it's the first 4 may be okay, but the others perhaps not. Looking at the Young box, that one's okay, but let's have a look at 8 lags. That was clearly significantly different from 0. And 12 lags. Again, a problem there. So let's have a look now at the third model that Enders tries. And this is a model, as you can see, 011, 011. So there's no autoregressive elements here. They're both moving average, one at lag 1, a normal one, and one at lag 4 here, a seasonal one. So again, I'm specifying the sample period, a subset here, so that it's at the same, every model starts at the same period, so that it's over the same sample period. Remember, you have to check that here. I didn't need to do it model 2 because that has the longest sample period, so the others, the shortest I'd say, so the others had to be restricted to make sure they agreed with model 2. So running model 3, here are the results that Enders gets. As you can see, they're both moving average, one's at lag 1, a normal one, one's at lag 4, a seasonal one, hence the S here. Let's find the various goodness of fits. Residual sum of squares, again that's higher than model 1. AIC, again higher than model 1. SBC, again higher than model 1. As you'll see if we just check back, here's model 1 here. let's just check the residuals, but even if these are okay, model 1 would be preferable, but here's residuals. So that one is certainly a problem, as you can, it's not surprising here given this. So 8 and 12 will probably also be problematic. Yep, these are massively significant, different from 0 with those very, very low p-values. And then like 12, again, a problem as to be expected given this pattern of individual ones here. So it looks pretty much, and this is what model Enders himself concludes, that model 1 is the best of the 3 models here, the ones he thinks are a reasonable fit to the data. So let's have a look at, let's forecast from that model. Now remember I looked at this in the previous video. You can easily do this if you've used the forecast package and the ARIMA function. It's very easy because you can simply put the model results here. So I'm taking the results of model 1, which are in this variable model 1, model underscore 1, and then piping them into forecast, specifying that I want the next 12 periods to be forecasted, and then you simply pipe that into autoplot. These functions, forecast, autoplot, are all in the forecast function, and that, as you'll see, will generate a nice graph with the forecasts and with prediction intervals, and looks very nice. It's very easy and neat way of doing this. So, and there we are. So there's the actual data, of course, again, and those are the forecasts with these prediction intervals. So it's very, very nicely done here in the forecast package. Now, you could, of course, as I mentioned in the previous video, use the auto.arima function in the forecast package to automate this process and hopefully find the best model very, very quickly by letting the package do all the work. So I've done that here. So I've taken my data, M1, of course, is my variable with the data in, then piped into logs. So again, I've taken the log, of course, as we did, and then I've simply piped that log data into AutoArima, and in order to make sure it searches as thoroughly as possible for the best model, you set these two values here, approximation and stepwise, to false. If you miss those out so that they're true, it will still search for the best model, but it will use some shortcuts. So I want to make sure that it's as thorough as possible and to see if it comes up with the same best model that Enders did, which was model 1, of course. So running that, we get this. Now notice that it's in fact decided that the best model is 111011, which is different from model 1 of Enders, which, if we go back to it here, was a 110011. This is a 111011, so it's slightly different. It's same, agreed on the seasonal pattern 011, so it's agreed that we need one seasonal difference and one normal difference. It's agreed that there's a hiss 011, but here it's going 111 rather than 110, which is what. So this believes that there should be an additional normal MA element there, which Enders didn't. So it's not coming out as quite the same model. Now, is it better than model 1 in fact? Has this done actually better? Well, let's test that. I'll estimate this model manually so I can check the SRC and the residuals and so on, the AIC I should say, and then we can compare them. So here I'm running using the same thing, calling it model 4, so we're starting with the data, logging it. Again, I need to restrict the sample, so it's the same as Model 1. Putting it into ARIMA with these things specified, 111, 011, method CSS. So running that, I get the these coefficients. Now these are different here slightly because the auto ARIMA did not restrict, use the whole sample period, whereas I've restricted it in order to, it uses the same sample period as Model 1. So finding the residual sum of squares, and I noticed that is actually slightly better than Model 1. Model 1 was 0.177. This is 0.175. It's close, but it's slightly better. Just if you go back here to Model 1, 0.177. So that was better. Notice the IAC is minus 735. So what do we get for this? 735,398, which again I think is slightly better. Back to Model 1. Yep. And I believe the SBC is also slightly better. 722. So in fact, the auto ARIMA function here seems to have discovered a slightly better model than Model 1. Although there really isn't much in it. If we, assuming of course that the residuals are okay, let's check them. So they are fine, yeah. In fact, they look fine. There's only that one there again, very similar to Model 1. The p-value is fine on 4 lags. What about 8 lags? That's fine. 12 lags, that's fine. So the residuals are fine. So it looks in fact here as if the auto.arima function has discovered a slightly better model than than using the manual approach of Enders. Now that doesn't always happen. Again, in the previous video where I tried auto ARIMA, that wasn't the case, I believe, but here it does look as if. So it's worth trying the auto ARIMA function. So let's finally forecast using Model 4. And those are the forecasts. Now you find, in fact, that these are, because the models are very, very similar, the forecasts look very similar indeed. So this is Model 4. Let's go back to Model 1. And as you can see, there's it's difficult to see any particular difference here. So Model 1 or Model 4 would seem to be the best ones here. Okay, so that shows you how to do some modeling of seasonal data, ARIMA modeling of seasonal data in R. So if you want to know more about the forecasting package and the various forecasting procedures that it contains, including ARIMA modeling, then you can do no better than going to the online textbook by Rob Heinemann and George Athanasopoulos, if I pronounced that correctly, which describes all the various procedures and is also a textbook teaching you how to do forecasting. It's an excellent resource which is well worth looking at. Now it's important that if you want to look at the forecast package, that you go to the second edition site. There is in fact now a third edition which uses the new packages which Hyman and colleagues have put together for forecasting, which is based around the tidyverse. So if in fact you are more concerned, you would like to get more into using the tidyverse, then maybe you should look at the third edition of this text. But both of them, second or third edition, are very, very useful.